Hi, my name is Vladimir Lazarev, and I am very interested in programmer-friendly and highly performant IPs, which may orchestrate execution on different units of the device. I'm glad to present Abhilash, who will present how the C++ work group is moving to the world where the standard C++ is enough to get spread computations to all execution units in your device. Now, I would like to let Abhilash start his presentation and present all the new stuff which we are going to see in next standards. Please follow.
Thanks, Vladimir, and a very warm welcome to everyone. So today we are going to talk about parallel range algorithms, and I'm Abhilash from NVIDIA, and I'm also a member of the C++ working group 21, which is focusing on SG1 and LEWG. So today we are going to cover a brief overview of what went into STD execution and what is the current state in the STD execution that is going to be in C++ 26 and eventually in 29. So we are going to start with STD execution. That is the basis of the foundational concepts for our talk today. It is going to focus on P2300, which is the start of the execution plan or the namespace. We are then going to go to C++ parallel algorithms, which is P2500. We are going to venture into parallel range algorithms after that, which was built on top of it to enable parallelization on range STD algorithms. Then we are going to move to some industrial use cases, which is 1DPL and thrust, which uses these concepts for parallelization. We are going to move and learn a little more about what went into C++ 26 Hagenberg meetup, which happened on February, which is the latest update from the standard committee. And we are going to end with some question and answers. So moving forward with the first part of the talk, which is the foundation, which is STD execution, P2300, led by these great folks. And STD, the library in the namespace, we have parallelism and concurrency introduced in different ways. So in C++ 2017, it started with standard concurrency and parallel algorithms that we have. So that includes std-par, std-par and sec, and different kind of parallelization algorithms. We move forward to C++ 20. We have new things called as concepts, ranges, and modules as well. So the ranges introduce new things like std transform, std reduce, and so many different algorithms. Moving forward to C++ 23, where we had new algorithms added to ranges plus. That includes different kind of transform, reduce, as well as different kind of variations of these STD ranges. We also have multi-dimensional spans. And we are currently now moving towards 2025, towards 2026, and we have already finalized most of the stuff that is going into C++ 2026. We have the executors, that is the senders receivers concept. We have papers like P23002500 and follow up on P3179, the sixth revision. We have some papers from reflection going in. We have a lot of things coming into algorithms. And algorithms and linear algebra like P2630. We have concurrency. We are going to have a lot of concurrent queues as well, and new features which are going to come up in P0260. SIMD is going to be a lot more beneficial and user friendly. In the standard library, there will be a namespace change. And of course, there are safety concerns as well. So new papers are also getting published in safety or in MISRA. We are going to focus on the executors, senders, receivers. That is the first part of it. And let's get started on it. So why we needed P2300? What was the need for that? So the need is for a flexible abstraction layer that answers where the code should be executed. Previous to P2300, there was nothing called as an execution context. That means where your code should get executed. This paper adds this feature specifying the hardware also where you can execute a particular piece of code. Now, this mimics STD future and STD promise concepts where you can perform a lazy invocation or perform an asynchronous task through a lazy mode, and you can schedule it on a specific piece of hardware. And now, previously, we did not have this support for accelerators. So let's say if you're running on CUDA accelerators, if you're running on AMD accelerators or different accelerators, it would not get executed. So C++17 is actually the parallel algorithm support was a good start from where this entire thing started. We and there was some limitations of P2300 in terms of the execution hardware. So let's say context switching between different execution hardwares like CPU, GPU, or GPU, GPU, and there was a need to integrate schedulers with parallel algorithms. So that is where the concept of senders and receivers as well as schedulers came into the picture, where P2300 introduced this parallelism to counteract this effect of having this execution hardware. So P2300 also introduces the scheduler concept, which represents where we want to run our target hardware, the code on a particular target hardware. The integration of these two parallelism concepts as well as the execution context is very much beneficial so that it allows us to run on different hardwares. So the main features is senders. Senders are like packets of asynchronous tasks which gets executed through agents. So these can be forked, joined, and these are also awaitable. They are also lazy. So you can have a sender do pre-compute something and wait for some time, which is a lazy execution. Senders can be single shot or multi-shot, which implies that you can pipe different senders with different transformations, or you can have a single shot sender combining them as well, one after the other. So there are different kind of sender APIs as well, known as sender factory APIs, sender adapter models, and all of them are, they support different kind of error handling mechanisms, exceptions, cancellations, and so on. We'll be looking at some of the sender factory APIs after some time. These adapter models are actually lazy as well, so that it gets triggered once your entire asynchronous task has got completed. So this essentially means that your senders is going to have senders are actually like the tasks which get scheduled, and you are going to have an orchestrator, which is known as the scheduler, which is going to execute all the tasks and maintain the synchronous behavior, like having a barrier and maintaining all the synchronous behavior at the end. Receivers are like the glue between the senders. That means, let's say you have different senders which are performing different tasks. So let's say you have a task for reading a different file in chunks, in data parts. So you are going to have, let's say, different threads or different collection of threads performing that reading. And you want to have those receivers to compile different outputs of those individual threads performing the reading. Like, so this kind of things is known as a pure sender and receiver, where the senders are performing the task and the receivers are the particular glue and getting the output of that particular task. Execution context is a customization point and is also the orchestrator between the senders and the receivers. So lazy senders provide optimization by fusing multiple ops, like I talked about. So you can pipe them or you can fuse them together via an execution context. And there is also a possibility of customization of transfer with schedulers. So let's say we are doing context switching between different CPUs and GPUs, right? For the same piece of code, we need to have a customization point so that we know what sender to send to, what sender details or data should be received and interpropagated to the CPU or interpropagated to a different GPU and so on. So introducing schedule from the adapter is another important concept to enable full customization, both by the source and the target schedulers. The proposal also introduced a schedule from adapter, which allows the schedulers to customize the transition. So this is what a typical sender pipeline, sender receiver pipeline looks like. So you have the sender, which is just hello world, right? And inside this, the task of that sender is just to provide a flush print on it on the screen that it is just a hello world, right? And the scheduler is just the CPU scheduler, right? You can see that the loop.get scheduler is actually coming from the standard CPU thread, and it will create an execution context or an execution context which is denoted by the scheduler, and inside that scheduler, which will orchestrate the sender to perform that particular piece of work, which is just nothing but printing it through a lambda. And you see the auto result at the end. This is specifying that this thread, sync wait, it will synchronize until that entire message, which is the hello world, is flushed from the system, right? And after that, the loop will finish and the worker joins to the main thread and we get a return 0 at the output. So this is how a particular sender, scheduler, and a receiver framework kind of work together. A very simple example. Now, we'll be coming to more complex examples sometime later back, but we are also having another example. So let's say we were performing a scheduler to actually do some computation for us. So we are initiating a scheduler, which is a thread pool scheduler, which is a CPU thread pool scheduler. You can have a GPU thread pool scheduler as well. So you are creating a sender auto begin, right? You are initializing the scheduler, and you are creating a high lambda, which is another sender, which performs certain computations. So hello world have an int, which takes from the input. So it is going to return 13. And the next sender is going to perform another atomic tasks, which is just adding 13, adding 42 to 13, right? Adding 42 to the input argument. So they are all working asynchronously. Each individual senders are performing asynchronously. So we need to have kind of like a barrier or a synchronization point. Now we do this by specifying this thread sync wait. And we call wait on the add 42 sender, so that until the 42 addition happens, we can make the threads wait for it. And after this is done, we can release it to the receiver end so that the output gets printed. And everything is orchestrated by the thread pool scheduler context. So we saw another example of this. Now moving to the sender factory APIs. So there are some APIs which helps us to customize the granularity of effort and also computing that we can have with the help of these factory APIs. So I will go through some of the major factory APIs only, which are essentially needed. So for example, you have the auto scheduler, the just and the schedule API, which is vital. So whenever you have a sender auto schedule or you have auto just, so this instantiates the sender as well as the scheduler context on which that sender is going to run. That means it essentially creates the entire task graph for you. And it will create and allocate that sender process ID to that particular scheduler. So for example, you have this get system thread pool scheduler on the right-hand side, where you are creating a systems thread pool. And inside the thread pool, you are going to create a process, and you are going to create an association of that particular sender, SND1 in the example, by using that auto schedule and auto just. So there is also one other thing important to be noted, that you can either perform std move on some of these sender operations, or you can also perform a decay copy to it. For example, in the last few lines in the right hand side, you will see execution sender auto SND1, execution just 1F. So this will imply that this particular SND1 will execute with a value of 1.0F, and whatever computation it needs to do is mentioned inside SND1. You have some error handling mechanisms as well. Like I said, the sender factory APIs are very much strongly worded for handling different kind of exceptions and errors. So you have transfer just error, and just stopped. So transfer just is one other API which gets the system thread pool, and it passes in a variadic arguments to the particular sender. So it can have, so let's say here I'm just doing addition, let's say, right? Or you can just, here the receiver is just taking the values 1, 2, 3 from the input buffer stream. So these variadic arguments can be put inside your transfer just. So it will take the entire piped or the piped in buffer from the input buffer, and it will just send it to you to the particular sender, right, in the particular execution context, as it is, without any, through a copy operation. Actually, this is actually a copy operation, and we can use this to do some console logging. So let's say some std print args, where we are passing those args in a lambda kind of sender, right, in the example. And we have, and just to ensure that there are no breaks in terms of IO buffer transfer, we have the just error and the just stopped as well, just to prevent that. We have another important set of APIs, which is the upon and the let APIs, which essentially tells you that you are going to have the sender, where the task graph is actually created. You are going to add an invocable. So invocable means that when, let's say, you are passing the data from the input args, so it becomes an invocable. So when you are using the upon API, you can essentially pass in args at runtime to the sender that you have created, and it becomes an invocable API. So you are also going to have let value, error and stopped, and other similar values to get into the particular sender. But the difference between the upon and the let is that let returns the sender with a callback, right? So this is almost similar to having std future effect. So that means you are going to have a callback or a record in the stack trace that you have pass these arguments to the sender. Why this is important? Because let's say there is some asynchronous behavior in a particular hardware, and some threads get out of line. So in that case, you are going to miss on certain vital values. So to avoid that, you have let value, which maintains a stack trace, which maintains a callback to the wrapper in a lazy manner, right? So that your values doesn't get changed or modified in any other way. You have also some important adapter APIs like on into variant and bulk and split API. I will be talking about bulk a little bit later in a broader context. But on and into variant will provide the sender on an execution context belonging to the particular execution hardware, right? Into sends a variant of the tuples of all the possible set of types sent by the input sender. So it does an abrupt combination of all the types which is sent to the sender. Bulk is like sending chunks of data, like almost similar chunks of data in a piped manner to the particular sender. And we'll be looking at bulk in a short while in more details. Split returns the sender if the provided sender is a multi-shot sender. So let's say your sender has a lot of tasks under it. So it delineates, let's say it does reduction, it does transformation, it does addition, and so on, different, or let's say, or any kind of IOTA operation, right? So this is multi-shot kind of a sender, and you are sending all the data to it at one time. There are again some other APIs which are not that much, you can use them, but in terms of priority, they are also kind of important, but not as much. You have transfer when all and ensure started and when all. So as the name suggests, these ensure that your sender has received the particular kind of data to the particular execution context and it is executing it. Right? When all returns a sender that completes once all the input senders have completed. It has a constraint that only accepts senders that can complete with single set of values. So with multiple calls or multi-shot senders, we cannot use when all. And ensure started implies that your sender has started. It gives a signal or a flag check that your execution context is running that particular sender. Start detached and this thread sync wait. This thread sync wait is very much important because it is the sender consumer orchestra, mediator, or kind of like the barrier which performs the synchronization in place so that every thread is synchronous beyond that point. And it is needed in almost every kind of code example that we see. Ensure started is another kind of similar meaning to start detached, but it does not return a value. Okay, so if the provided sender sends an error instead of a value, the std terminate is called. So it does not send a value or a flag check like the ensure started, but start detached just sends a terminate signal. Now, once we looked into the adapter APIs, now let's move into the sender consumers example. So let's say a piping example, which is very popular of a multi-shot sender. Here we are doing a kind of like a sender which is working on an execution schedule, thread pool schedule, and you are just returning 123. In the next case, you are piping that particular sender in the next line, and you are creating a new stream from CUDA, from the CUDA scheduler. Now, this CUDA scheduler with the execution is then returning 123 multiplied by 5. And after that, you are transferring this CUDA thread, I would say, sender back to the CPU, CPU sender. You are transferring this data back to the CPU sender through a different execution context, right? And you will see that there is a thread pool scheduler, there is a CUDA scheduler as well. So the thread pool scheduler is part of the CPU context. So there is a context switch which is happening when sending the data 123 multiplied by 5. And once this is done, you can get the receiver will get the data as 123 multiplied by 5, which has worked on the GPU or the CUDA. And this thread sync wait, we are going to get that value. So this is an example where piping, fusion, and transfer of CPU to GPU work and back from GPU to CPU work is happening. Another complex example, and I will give some time to go through this, is that this is an asynchronous read example where what it means that let's say you are reading a very big file in chunks, right? And these chunks are going to go into the memory in buffers of data in one let's say buffer 1, buffer 2, buffer 3, and so on. So how you can mediate this using STD execution senders and receivers. So async read is pipeable sender receiver which reads in spans. So you are going to read in span format. The idea is you can see that the sender off in the second paragraph on the left hand side, you are going to return a just invocable that pipes different operations one after the other. So you are going to have let API, which we just saw, let value, right? It will take the dynamic buffer entries. It will return a writable bytes from the buffer, okay? And async read function is then called. Async read is one of the other sender which actually reads that data is going to get called, right? And after that, we are using the then API to check whether the amount of bytes that we have read is actually this, the size of is correct or not. We do a kind of like a checking, and if it is correct, we populate the buffer.data, that is the buffer data structure, dynamic data structure, with the input from the IO buffer, right? And we return the STD span buffer.get data buffer size. And yeah, that's the entire loop in a nutshell that is happening. So you're using let, which ensures that you're picking this sender to be on this particular execution context. You are returning just, which is we are returning a span actually in that particular execution context for that particular buffer read, and you are reading it, and you are checking the bounds, and then you are writing that data inside this buff.data data structure, right? And this entire flow is happening at a parallel manner. At the end, there is a thread, this thread sync wait, which needs to be added. So this is a simple senders consumers example where you are chaining, you are using the adapter APIs for lazy propagation, and you are doing an asynchronous read. Another example, inline scheduler. So this is a very complex example. So also taken from the paper P2300. So here we are doing an inline scheduling of different tasks, right? And we are performing a scheduler in place as well. That means whenever we get a kind of like a pipeable multi-shot tasks, right? We are piping it one after the other. Instead of propagating them lazily, we are doing it inline. So it schedules one operations after the other inline. Now, this is a kind of like a broader in-depth implementation of how this is working. So one major thing to note is that you are going to have an environment which loads that particular scheduler, and inside that scheduler you're going to have senders. Inside the senders, you are going to perform different completion inline, you're going to have completion signatures which perform all of those operations inline. And once those operations are done, you can pass it to the receiver. So this example is from P2300. It's a little bit complicated example for inline scheduler, and I would suggest to go through it in the paper as well. So moving to the next part, which is C++ parallel algorithms by Ruslan in P2500. So why P2500? Now, till P2300, we had a very good concept on grasp on the hardware execution context, and we could execute everything that we want, right? Now, we needed to have a flexible abstraction that we can run the hardware on, but also represent the scheduler concept, control that I want to run this part of the parallel algorithms. Let's say std_par with execution context as CUDA, right? So that was missing. So parallel range algorithms, or rather, I would say C++ parallel algorithms with the execution context basically means that you have the parallel algorithms in place, right? So you have std_par, std_par unsec, and different kind of parallel algorithms. Now, those parallel algorithms till before P2500 were not having that execution context in place. So that means you cannot leverage that feature in C++. So now this particular paper adds that. So how the changes have evolution. So you see the C++ 11 to 14, you have namespace stde, which is the execution, and you could specify a vector or any other kind of data structure, right? In P3179, which I will talk about a little bit later, you have ranges which support std_par. In P2500, you have std ranges, and let's say ranges followed by any kind of operation. Let's say here we have taken sort and generate. We are specifying an execution context plus the parallel algorithm that we want to run it on. So you have std sequence, here we have parse. You can also perform part unsec and with execute on as well. Okay. So the proposed solution proposes extending C++ algorithms to policy-aware scheduler. This scheduler combines the execution policy of how and where. That means where was denoted by P2300. Now you have how. That means which algorithm do you want to run it on? So do you want std_par, std_par unsec? The execute on is a new functionality or a new feature which got added to these policy-aware schedulers. Extending C++ parallel algorithms with policy-aware schedulers, allowing customizations of different execution contexts, and also make it backward compatible and preserve the classic ranges algorithm. Okay, so why use schedulers? Schedulers represent execution context and provide flexibility. You have three key concepts introduced in this particular proposal. You have customizable functions, you have execute on, you have policy-aware scheduler. Okay, And we'll be looking into that a little bit, examples in mind. So the first one, policy-aware scheduler. So here on the left-hand side, you see the API example. You have a concept policy-aware scheduler, which requires a concept S, where S is of concept-based type scheduler, and s.getPolicy is the API that you are going to invoke in a particular execution policy. Now, how to use it? So the right-hand side shows you the usage example as well. So you have struct my scheduler. So you have let's say you have a base scheduler, let's say get CPU scheduler or a thread pool.get scheduler or something like that. You are using a policy type. Now, what policy type do you want to run it on? So this policy type will inherit from the system policy type that you have from the API example as below. And then with that policy type, you are going to bind to that particular scheduler. So now with the scheduler, you not only have the capability to add senders as well, but also you have the capability to add a particular policy. So this is another example. So here, this tells you execute on, how the API and the usage of execute on is going to happen. So the left-hand side gives you the inline namespace of execute on, which is a const expression execute on function. On the right-hand side, you have the policy-aware scheduler, std execute on my scheduler. So here you see a very beautiful thing where we are combining the features of P2500 and P2300. So you have the my scheduler, which is your CPU scheduler or a GPU scheduler. Along with that, you have the std execution policy as well. That means par or par unsec, whatever you want to add it on, right? So this is the execute on customization point where you can use, combine these features. And this is the API change, which is propagated for versions. You have the existing API, which is the execution policy, iterator, and a class function. Now you have the new policy-based API, which has an execution policy, iterator, sentinel, as well as a projection, right? And in the next case, you have a new scheduler-based API, where you have the policy-aware scheduler, input iterator, sentinel, and also a projection. So as we know, projections is like any kind of the data structure that we want to apply our transformation on. Okay, at the end we have a ranges scheduler, right? We can have a iterator and a sentinel as default, and along with the scheduler also we can have a kind of a policy as well. So yeah, this is another example to look into. Allowing schedulers with C++ algorithms, and it also performs blocking behavior similar to C++17 parallel algorithms. So as you know that if we talked about P2300 where we discussed on this thread sync wait, which is like a kind of like a blocking behavior. So same concept is inherited over here as well. So another example for you to view. You have a scheduler, you have a forward iterator, and a sentinel, I guess a forward iterator last, and a function f. And inside that scheduler, you're going to have a lambda which executes a simple loop, right? Where f is a function. So any function, it can be std ranges reduce or sort, anything like that. Using the API. So std for each, std execute on your GPU scheduler, what policy you want to execute on, std execution par, your data structure, right? Your iterator and your sentinel, and the lambda that you are going to perform. So item.process is your lambda, what you are going to perform on the data structure, right? So this is an invocation where you bind P2500 to std for each. Customization and extensibility. So let's say that was on the CPU side, on standard C++. What if we want to do it from the CUDA side, right? Or on the acceleration side? So here you see namespace CUDA. This is taken from Thrust actually. You have struct scheduler. You have a const expression auto tag invoke, right? And inside that you have a CUDA optimized implementation, right? And inside that CUDA optimized implementation, you are going to perform a ranges for each, right? So this gives you a kind of like extending the I would say the ranges API through execution policy, through parallelization policy, right? Inside CUDA. So covering both classic and range algorithms, support for both types, right? We saw a ranges example in the first, and then we saw a classical example as well. Parallel and range-based algorithms integration with schedulers. Default and customized implementations using tag invoke, just the example that we saw in CUDA. Extending existing functions with new constrained overloads and code snippets for each, right? An example for you. So how we can perform for each function, right? Using a policy-aware scheduler, an input iterator sentinel, and a projection, which is a function, right? you see the scheduler and getting and let's say inside if const expression tag invocable, I'm doing it inside the CUDA, so you can also add the CUDA part or any other accelerator code as well over here. So for example, std tag invoke for each function scheduler. If you pass in the GPU scheduler, it will perform that thing on the CUDA as well. We already know the benefits as of now. So unified API for different execution contexts, optimized implementation per platform, and extensible to future scheduling needs, and covers both iterated and range-based solutions. There were some open questions, and I will come back to this slide later because they are all, most of them are now handled. So parallel backend and customization approach is now handled, and so on. So now we know the summary of P2500 and 2300. Let's move to P3179, the most interesting part of today's topic, which is parallel range algorithms. What is P3179? So firstly, in C++26, it is approved. So this will also get added, barring some wording changes in version 7. So the parallel range algorithm should be close to C++17, where it introduces STD algorithms, ranges algorithms to use the parallelization concept. The parallel range algorithm should return the same type as corresponding to the serial range algorithms. So there should not be any counterpart that the parallel ranges and the serial ranges invocation is different or the template is different. It should be the same. The proposed algorithm should be non-ADL discoverable functions and same as serial ranges. And it should cover all the categories of STD execution, that is sequential, par unsec, right? Parallel, right? Execution policies. The proposed API should require any callable object we pass to an algorithm to have a const qualified operator. It is not a customization point and it is not a const expression. Currently, in P3179R5, till now, most of them are part of this, have been added to this in a very repeated manner. There are some wording changes needed for partition copy and copy start, that is copy for each and copy for n as well. But most of them have the parallel ranges support. Now, the API design. The left-hand side was the before API. We have STD for each, STD execution par on a data structure. And after, this is how it changed. So STD ranges for each, STD execution par, right? V begin, V end, and you can pass in the auto lambda where you can perform the different operation that you want, or you can use the ranges directly. STD ranges for each, STD execution par, and the lambda or the functional lambda that you want. Another example. So it gives you more expressive and unified calls. You can do piping as well. See, before with the API, you have to write 3 different lines of code to perform reversing on an iterator container, and then transformation on it, and then get the receiver end using an autores, right? Using any of. Now, you can do this in one piping operation. You can do any of, reverse, and then transform in just a piped manner on the same data container and return it to an autores, right? Using any kind of STD execution, the algorithm that you want. How is the design changing? So we start way back from C++3, where you have a very crude implementation. We move to C++17, where it introduced the STD execution policy we talked about. In C++20, we saw random access ranges getting added, right? And the class comparator as well, and the class projection. In C++26, this is where the new one gets introduced. You have class execution policy, random access ranges, right? And and the rest of the arguments remains the same. For example, in the last line, you will see const expression borrowed iterator t range is sought. Where you're performing an execution policy, you are sending an R, which is the random access range, and you are providing a comp as and a projection. So why combine parallelism with ranges? Now, ranges offers a lot of customization and a lot of parallelization features in place. Why not use that? And a lot of optimizations in place. So users are already using ranges with non-parallel range algorithms. So it makes sense to integrate parallelism and ranges. The power of ranges and parallelism is now part of actually C++, will be part of C++26. And, and previously did not seamlessly integrate, but now it will. And users are going to use it not only on the CPU, but also any other hardware accelerators, because this has support for all backends. Key modifications, we talked about execute on, random access, bounded ranges. So yeah, this one, the third point is very much important, is that the ranges needs to be bounded. It is not that if we have unbounded ranges, there is some issue. and that is currently under debate. And the algorithm return types should be consistent with serial range algorithms. The return type should be consistent. It should not be different. This is an API design which went into this. Just for an example, we already covered this. So, for example, an execution policy with a random access range R and a projection with an unary invocable. You are going to have you can have a design API design like this, where you have ranges for each with those arguments in place, right? But the template design is going to have a indirectly unary invocable. Let's say I'm doing for each over here. So yes, it is going to have an invocable over here, and the rest of the arguments as it is. So it will preserve all the C++17 algorithms. It takes range as output as well. Before that, you did not have the capability to return ranges as output. Now you have the capability to return range as output, and return types match the serial range algorithms. There are some differences. Parallel range algorithms require random access ranges. Output can now be a range instead of an iterator, and all input and output data sequences must be bounded. Another example we saw this a little bit before. So skipping this slide, this is just the piping operation we saw about. We already talked about the benefits. So this will enhance the expressiveness of the code as well, and safer APIs, because we are performing boundedness now and range checks. Yeah, the latest status. So in C++26 for the R6 revision, so for the copy operations, that is copy for each n and copy others, right? Wording was directed to modify the behavior into return the first element which wasn't copied to comply with the predicate or the sentinel. For each operations, there were some wording changes needed, but in this case, the existing overloads can be expanded with the execution policy. We do not need a ranges counterpart for this. For most of the algorithms, merge, partition copy, rotate copy, there is a wording fix needed in R6, which would handle corner cases. Corner cases being that the first element from where the partition is going to happen or where the copy is going to happen, a bound on that particular case, whether we want a strong bound or we want a weak bound. That is, let's say till ith element, the I minus 1th block was getting copied. Now, should we start from the I plus 1th element or not? So wording kind of like changes were introduced in this case. Now let's move into the industrial use cases, which is a broad specification of how these are getting used in the industry. We'll go with the Thrust. Thrust is a standard. Thrust is a CUDA library, which is inspired from the C++ standards library and built on top of OpenTPP, OpenMP, TPP, and CUDA. Right? So it has different kind of parallel algorithms like exclusive scan, inclusive scan, reduce, for each, gather, and so on. Right? How to use that? So you see the examples that we saw before, and now in Thrust, how you can use that. So template implementation, you have the derived policy, which is a Thrust host system namespace execution policy, your CPU execution policy, and now you have your device execution policy, right? So on the right-hand side, you have the API usage example. So struct my policy Thrust, host execution policy my policy, and you are going to perform, let's say, transform my policy on the data structure, which is the standard data that you have, right? And it will automatically handle and create the scheduler and the execution context for you. Similar things are also part of 1DPL, which is the parallel STL from Intel. So it works on the SQL programming language, and it is providing a mapping for the SQL kernels and macros, and not only on the accelerators, but also on the FPGAs and on the CPUs also you can use it. Here, the namespace is a little bit different. It is known as DPCPP, DPCPP default and DPCPP FPGA. So they have been added to the STD execution in Intel under Intel namespace or 1DPL namespace. So for example, if we do STD fill with 1DPI execution policy par and sec on the data structure. So here on the right-hand side, you are going to have calling device policy for SQL GPUs, which is Intel GPUs, right? You can just specify the device on which it is going to run the execution policy on. And here we are going to see the STD for each, and also the ranges as well. The ranges support is also there. And we are going to have DPCPP default, which is going to run on different default DPCPP device, right? So you see the examples from P2300 all the way to 3179 getting used everywhere. And as such, there has been, actually this started from the industry side and it went back to the C++ standard side as a kind of like a proposed approach. The last part is the Hagenberg update. I want to keep this point. since our last standard committee meeting. I wanted to specify what went in and what is going to be added to the senders and receivers, as well as SIMD. So asynchronous senders, as we know, is asynchronous execution facilities on concurrency models. So P3179 we already talked about, strongly favored with wording changes. P3564R0 is working on bulk execution. So STD bulk execution bulk is a kind of algorithm which does which schedules senders in bulk format, right? And this does not guarantee safety in terms of forward progress. Like concurrent forward progress, I would say. So let's say you have 2-3 different centers with bulk executing on the particular context, right? Execution context. So who will guarantee that this concurrent execution is moving is having a forward progress? That means that there is no overlap or there is no skipping or incoherency when it comes to the receiver's end, right? So blocking execution is very much essential in this case where you have the STD execution bulk. It maintains the concurrent forward progress guarantee, and it has got a favor to have new additions. P3481 had suggestions to improve some of the issues on bulk execution on STD execution bulk, such as making bulk unchunked not dependent on the execution policy. Bulk unchunked is another API where you have the capability to unchunk parts within your center's bulk API, right? And making it non-dependent on the execution policy also makes it very much asynchronous in nature, right? And that is the decision which was actually taken. But there are some stuff needed to be done over here, some corrections needed for 3481. P3552R0 was adding concurrent lazy coroutines for STD execution tasks. So as we know, STD execution tasks are similar to centers, but they perform atomic tasks. And the proposal adds, coroutine for, lazy coroutines for that. P2079 and 3624 suggest changes to the system execution context. That means should allow users to replace the parallel progress guarantee system scheduler and must return a concurrent progress guarantee. So that means that the ordering in which you're running your senders in an execution context must be preserved. Okay, for any kind of systems, not only for the standards systems that we have in our CPU, but also on our accelerators. P0260R14 added some details on concurrent queues and enabling communication across different components you have for embedded devices as well as signal handlers. And it is well suited and integrated with the centers and the coroutines namespaces. So these were some of the major papers. There were also some other papers from SG1, which I skipped. For SIMD, there is going to be a name change for SIMD. STD SIMD is not going to be there anymore. So you're going to have STD data part, and you have the capability in SIMD to do implicit conversions as well. So extending SIMD with permutation API is advocated in P2664 by Matthias, and P2876 adds more constructor to SIMD for conversion between span and bit set. So this conversion would help to perform implicit long to bit set conversions and so on. And this is essentially important for some of the intrinsics in which uses SIMD. P3319 advocates for IOTA object in SIMD. So these were the major updates from the centers and the SIMD side parallelism, which went into SG1 and also ADWG as well. So and that concludes the session for what I wanted to talk about today, and I will be opening up the floor for questions.
Yeah, thank you very much for your interesting presentation. Yeah, and while we are waiting for the questions, I just want to ask the first one. Can we try it enhance? Do we have implementations? And if yes, which devices are supported?
Yes. So we have the implementations. So what is happening is currently most of the hardware accelerators are having the implementations in some specific libraries, right? So these libraries are open source libraries, or some of them are closed source. Now in C++, if it goes into, for example, P3179 is a very interesting topic, and if it goes into C++, you do not need to perform or write any kind of custom code needed for your hardware. It will automatically be taken care by your std execution namespace, or by your std ranges namespace, or your let's say there were also new namespaces getting introduced, but this should broadly cover most of the stuff of asynchronous nature in this period. So if we are talking about implementations, I think what the trend is nowadays, most of the thrust or the APIs, or these APIs are going to move to standard C++ 23 or 26 kind of wording and API usage. I hope that answers the question. Yeah.
Yeah. Okay. Thank you.
I think
Also, okay. The next question is: you mentioned that C++ will take care about everything, and when we have a GPU device, for example, and we have this host device data movement, will it be able to optimize movement? And if we have some pipe, will it avoid transfer from host to device while executing several tasks?
Yes, very good question. This is the reason why the last paper, which is 3564, this was observed in some of the systems as well. When writing concurrently using bulk std execution, we observed that there is lack of forward progress guarantee. That means that we need to have a correct ordering in which the amount of bytes. Let's say you are reading a big file or transferring a big file from the host, or data packet from a host to the GPU. So this packet needs to happen, in order. In order, in the sense that the device to device transfer of the data needs to happen in order at the so that the receiving end receives the packets in order. It can be any kind of data, right? Any kind of deep learning data, any kind of HPC data, and so on. So that is why when we pass it through std execution bulk in chunked format, we have to ensure that concurrent forward progress is happening. That means the order is getting preserved. So previously there was an issue with this, because and that is why P3481 was raising this a lot of times, is that how do we ensure correctness in the transfer of data in an ordered manner from GPU like CPU or GPU context. So probably after in C++26, I'm hoping that this will get some approvals, and it will get added in the safety standards as well in Misra. But I'm thinking that. But currently, for now, our only resource is to use this thread sync wait APIs to perform this synchronization in place before sending it onto the CUDA accelerator, or to the SYCL accelerator, or other accelerators. Let's say from the CPU to the GPU, to ensure that it is coherent and it is intact. Data is intact. So yeah.
Okay. So, and one more key point, like data flow control. So does it guarantee that in out of order devices, everything will be executed in correct order, or the user must define these synchronization points?
Yes. Currently, the user has to define the synchronization points. That is a must. But when you are using APIs, let's say for thrust, for example, okay, so in that case, you do not have to worry about synchronization point, because it is inherently, it handles that inherently. But let's say you are building a very custom, you have a custom accelerator, a custom ISA, and a custom accelerator, and you are designing for it. In that case, it is safer to have a customizable synchronization point, or a barrier for every kind of receivers. So when you write auto receiver, right, and you pass in a lambda to perform a different kind of synchronization, you can do that. That is a much more safer approach until these papers they get added. Also, I want to mention is P3179R6, R7, which is going to be the next one. It will also have several changes which ensures that the chunking that you are going for, the copy that you are going for, right? The parts like should be in order. That is what the debate in the Hagenberg went in. Like, where should I truncate the first, and how should I truncate the second, right? And how should they be more ordered one after the other? There is also another paper, which is the concurrent queues paper, which had several kind of debates on whether how, let's say we are performing different pop operations, right? Who should get on different execution contexts? One is on the CPU, one is on the GPU. Who should get priority, right? And whether the let's say the output of those two pop operations should be put into another concurrent queue, which is residing on another GPU or another accelerator, right? How should you maintain the concurrency? How should you maintain the in order nature of that? Right. So the output of that particular discussion was that if a particular call, if a particular sender is requesting a POP1 first, it must come first. It should not be that in terms of when the scheduler is sending these asynchronous threads, it should not be that POP2 comes before. So although it is concurrent, but the order precedence should be maintained on different system execution contexts. So that is what is a broader level. Yeah.
Actually, there are a few questions about the syntax, like it becomes more and more complex. Are there any plans to make it more clear and back to the simple syntax? And one of the idea is to use Facebook folly approach. Do you know about it?
Can you say the approach again?
Facebook folly. Then and error.
Oh, okay.
Yeah.
This is a debatable question in the standard committee, and yeah, that is the reason why most of these papers are going back and forth with the wording changes. I don't think that P3179 will have any kind of changes in the API templates. It is already gone through. The newer APIs, there have been some API changes for making it easier, but currently the flow is such that the committee is more interested in having more words which specify what that particular thing does. So it is going to become more big than what we have now. So, for example, SIMD, STD, SIMD is now moved to STD data part, right? People wanted to have STD data underscore parallel. So it is going to increase, eventually, because there are so many APIs we are getting covered. For example, if I go to this slide, so you have parallel algorithms in ranges namespace for all of them, almost all of them, except some of them like lexicographical compare and uninitialized default construct and some of these APIs, right? So when you are writing this, you have to include what execution policy you are running it on, as well as the ranges algorithm and the STD execution algorithm as well. So and there is no way to reduce that in it. So partition copy is going to remain partition copy. There is no place to reduce that or truncate that. So there has been efforts to reduce the namespace, but I'm not sure if there is a consolidated discussion on it. Yeah.
Thank you very much for your presentation. Yeah.
Thank you very much. Thank you very much for having me. Thank you.